All right, this is Physics, Chapter 14, Lecture 1. This chapter will have 3 lectures. This lecture covers on your own problems 14.1 to 14.4. So going through your notes, the first term is electric potential, which is potential energy per unit of charge generated by an electric field. Now the voltage equation is one you need to memorize. It is V is equal to KQ over R. We used K and R in chapter 13, R being the distance between charges. Q, though, big Q is the fixed charge. The problems in the book might say stationary. Okay, we're going to be dealing with a moving charge in this chapter, which we didn't deal with in chapter 13. Okay, so just going through the bullets, K is the Coulomb constant, R is the distance between the static charge and the moving charge, Q is the static or fixed charge, and V is voltage, which is another word for electric potential. So electric potential depends only on the stationary charge, not the moving charge. The unit for volts is joule per coulomb, so energy per unit of charge. And that is a volt, which we just designate with V. And also in Q, you must, unlike chapter 13, you must use the sign, so it could be positive or negative. So that's another difference. So let's look at on your own 14.1. In your book, if you're following along, this is on page 459. It says a negative 2.1 millicoulomb charge is anchored so that it can't move. A plus 4.1 coulomb charge is placed 61 centimeters from it. What's the electric potential? Okay, so K is 9 times 10 to the 9th. Big Q, all right, that is the anchored charge. So negative 2.1 times 10 to the minus 3 coulombs, since it's millicoulombs. And the distance between the moving charge and the anchored or fixed charge is 61 centimeters. So that's 0.61 meters. So you can see we didn't include that 4.1 coulomb charge in this because that was the moving charge. And if you'll place that in your calculator, you get negative 3.1 times 10 to the 7th volts. Okay, so moving on down your notes, we have the potential energy equation. Okay, you'll need to memorize this one. And that is Q times V, where Q is the moving charge. And V is voltage that we just figured out how to calculate. Okay, so the larger the electric potential, the larger the potential energy. So let's look at on your own 14.2 and turn in your book one more page over to page 460. So that one says a 7.9 millicoulomb charge is placed 1.1 meters away from a negative 2.3 coulomb stationary charge. What's the potential energy in this situation? Okay, we know that potential energy is equal to the moving charge times the voltage. Let's get the voltage. It's 9 times 10 to the 9th. The stationary charge is negative 2.3. And the distance between the two charges is 1.1 meters. So that's a negative 1.88 times 10 to the 10th volts. Right, so now we can get the potential energy. That's the moving charge, which is 7.9 times 10 to the minus 3 coulombs times the voltage, minus 1.88 times 10 to the 10th volts, which is what you just calculated. So that's negative 1.49 times 10 to the 8th, and the unit for energy is what? Joules. Okay, so that is page 1 of your notes. If you need to pause and finish writing, go ahead and do that. Okay, let's flip over to page 2. So potential difference is the change in electric potential from one point to another. And I've got a paragraph in that bullet, read through there. For example, in a 9-volt battery, the difference in electric potential between the negative side and the positive side is 9 volts. If a charged particle moves from the negative to the positive terminal, the potential difference is positive 9. If it goes from the positive to the negative terminal, negative 9. Okay, so our equation that we're going to use, and this is what you'll use much more commonly in this chapter, is the change in potential energy is equal to the moving charge Q, little q, times the change in voltage. And the change in voltage is equal to the final voltage minus the initial voltage. All right, so since you're going to have a charge moving, you're going to have an initial voltage, and then the charge is going to move to a different position, and that'll give you the final voltage. All right, let's look at 14.3. We're at the bottom of page 463. All right, it says a negative 1.1 millicoulomb charge that is free to move is placed 45 centimeters from a stationary negative 1.8 millicoulomb charge. If the freely moving charge moves an additional 25 centimeters away from the stationary charge, what is the change in potential energy, and did it increase or decrease? Okay, well, let's get the initial voltage. That's K times big Q over R. So 9 times 10 to the 9th. The stationary charge is negative 1.8 times 10 to the minus 3 over the initial distance was 45 centimeters or 0.45 meters. So that's negative 3.6 times 10 to the 7th volts. I realize these numbers are just tremendously large. But we won't worry about the practicality of that, but these numbers are ridiculously big in terms of a real world. That's because these charges are huge. All right, let's get the final voltage. The numerator is going to be the same, K times Q. What's different is the distance. So we have 9 times 10 to the 9th times negative 1.8 times 10 to the minus 3 coulombs. It moves, all right? Now both charges are negative, okay? If both charges are negative, they're going to repel. So if it moves an additional 25 centimeters, it's going to be 0.45 plus 0.25. All right, 0.45 plus 0.25. So your denominator is actually going to be 0.7 meters. All right, if you'll place that into the old calculator, you'll get negative 2.31 times 10 to the 7th volts. So our change in voltage is final minus initial. So that's negative 2.31 times 10 to the 7th minus negative 3.6 times 10 to the 7th. So minus negative would be plus, and so you have a change in voltage of 1.29 times 10 to the 7th volts. So positive. Now we can answer the question, what's the change in potential energy? Well, it's Q delta V Little q, the moving charge, is negative 1.1 times 10 to the minus 3 coulombs. Change in voltage, you just figured out, 1.29 times 10 to the 7th volts. All right, so place that in your calculator and you'll get a negative 1.41 times 10 to the 4th, and that will be joules. So that's the answer on the change of potential energy. Did it increase or decrease? Well, it's negative, so it decreases. And that means kinetic energy increases by that amount, but the potential energy decreases by 1.41 times 10 to the 4th joules. All right, that's 14.3. If you need to pause the video and continue writing, go ahead. We have 14.4, also on page 463. This one is a little bit easier. It says a negative 5.6 millicoulomb charge that's been given a large initial velocity moves from the positive side to the negative side of a 9-volt battery. What is the change in potential energy, and did it increase or decrease? Well, if it moves to the negative side, the change in potential energy is going to be negative 9 volts. Okay, moved, excuse me, not change in potential energy, change in voltage. Sorry about that. Be a second to correct that. Change in voltage, it moves from the positive side to the negative side, negative 9. If it had done the opposite, moved to the positive side, then it'd be positive 9 volts. So what is the change in potential energy? So I don't have to go through all the final and initial voltage because I've already got that information. So it's negative 5.6 times 10 to the minus 3 times negative 9 volts. All right, and that's going to be, put that in your calculator, you get a much more reasonable number, 0.0504 joules. And since it's positive, that's an increase in potential energy. So that finishes the initial lecture. The homework that you are capable of doing after this lecture, you can do the review questions 1 through 6, and you can do the practice problems. Put those here, 1 through 3. All right, review questions 1 through 6, practice problems 1 through 3, and those are on page 485 and 486. All right, with lecture 2, we'll work a few more on your owns, and we'll see you next time.